Good morning. Well, it might not be morning where you are, but it's morning where I am. We are going to work on some more story problems. So we are going to start with this one where we have a wire that's 10 meters long, and we're going to cut it in two pieces. We're going to take those two pieces. One of them we're going to bend into a square shape, and the other we're going to bend into a circle shape. So we have a total of 10 meters of wire. And they're telling us that we're going to use x, which is the length of the side of the square wire, as our variable. So then we would clearly need four pieces that size to make up the square. So that's where this 4x part of our wire is going. So 4x of it is going to be made into the square. And then whatever we have left, we're going to bend into that circular shape. So when we bend the other wire into a circle, since we have 10 meters total, then we're going to use everything that's left. So 10 minus 4x is going to be bent into the circular shape. So some formulas that might be useful would be the perimeter of our square. So the perimeter is 4x because we're going around 4 times. And the circumference of a circle, normally we find circumference by doing 2 pi r, but we also know that we're using 10 minus 4x of our wire to make that up. So we can have this equation 10 minus 4x equals 2 pi r. We're supposed to be expressing the total area enclosed by the wire as a function of the length of a side of the square. So clearly, like, the area for this square is going to be length times width, so x squared. And the area for our circle, that formula is pi times radius squared. So part of the issue that we're going to have to deal with is the area for the circle doesn't have x in it. And so we're going to have to somehow figure out a way to use this circumference equation to replace that r. So we'll go a equals pi times radius squared. And what we're needing to do is replace the r in the radius, or the r in that formula, pi r squared, using this relationship. So I'll go ahead and start moving some stuff around. I can divide both sides by 2, which would give me 5 minus 2x equals pi times radius. And then divide both sides by pi so that I get radius equals 5 minus 2x divided by pi. Now I can replace my radius over here with that expression. So area for my circle ends up being pi times 5 minus 2x, well, that's an x, 2x over pi squared. I could clean that up a little bit, but for now I'm just going to leave it. So our total area for part A, the total area, which is what we're looking for, is going to be equal to the area of the square plus the area of the circle. And I just found the area of the circle was pi times 5 minus 2x over pi squared. I already had the area of my square as 4x. So when I add those together, that is area as a function of x, which was the side length of a square. So that is everything for part A, just getting that formula. Part B, we have to say the domain of the area formula. So B, domain. So a couple of things that we need to think about for domain. Remember, domain is the possible values for x. Now, theoretically, in this formula, you can see we don't have any domain concerns. Like the only things we've talked about for domain is if we have variables in the denominator, which we don't have, or variables under an even indexed radical, which we also don't have. So the function itself, the domain would be all real numbers. But we also have to consider that this is a real problem, and x is the length of a square, the side length of a square that we're working with. And we have a limited amount of material to make that up. So what we would want to make sure happens is that we actually have some wire to make each of the shapes. So we would want to restrict our domain so that the perimeter of each figure needs to be greater than 0. And so that would be the perimeter of the square and the circumference of the circle. Each of those should be greater than 0. So we know the perimeter of our square. That formula was 4x. So we got 4x for the perimeter of the square needs to be greater than 0. When you divide both sides by 4, that's going to leave us with x is greater than 0. And then for our circumference of our circle, I'm not going to use the 2 pi r. I'm going to use the 10 minus 4x piece of that. So circumference of the circle, 10 minus 4x, that also needs to be greater than 0, which would put us at negative 4x is greater than negative 10. Divide both sides by negative 4. Remember, when you divide by a negative with an inequality, you have to reverse it. So x would be less than 10 fourths, which simplifies to 5 halves. So overall, the domain for this function would say that x has to be greater than 0 and at the same time less than 5 halves. In interval notation, that would be from 0 to 5 halves, like that. Okay, part C. Part C wants us to graph a of x and tell for what value of x is the area the smallest. So we will use our graphing calculator to make that graph. Part C. We're going to graph y1 equals that formula that we came up with, 4x plus pi times 5 minus 2x over pi squared. Need to grab my graphing calculator. And in y1, we're going to put this formula for x plus pi times, I can do this. I can get that fraction. Remember, alpha y equals gives us a fraction. 5 minus 2x over pi in my parentheses and squared. Okay, I'm just going to put this in like standard viewing window. So zoom 6 and see what we can see. Okay, there we go. Let me just put a quick sketch of that on my page. So that looks like a parabola, which makes sense because if I would FOIL that out, I would have x squared. And remember that every ordered pair on here, every ordered pair has an x and a y coordinate. In this problem, our x coordinates, remember how we started out, Our x coordinates represented the length of a side of the square. And when we typed in our equation, y1 equals, that equation represented the area of the square. So our y coordinates are going to be the area, not area of the square, the total area. We'll just leave it that. Total area that's enclosed by the wire. And so they're asking us in part A, for what value of x is a the smallest? Since a is our y value, the smallest y value on this graph is going to occur right here at the local min. And that ordered pair is going to be the length of a side of the square, comma, area enclosed, but this area is going to be the minimum area, specifically at that local min. So then to find that, we go second trace, which is the calculate menu. We need option 3, minimum, and we do the left bound, right bound guess routine. And it tells me the ordered pair for my minimum is 0.929, comma, 6.858. So they've asked me to say for what value of x is the smallest, and so that answer would be the x value. X equals 0.929. Hey, guess what I just realized? This whole time, you probably have noticed it all along, but this whole time I've had the perimeter of my square in this formula, so that should actually be x squared, not 4x. And so that would make this x squared, not 4x. So that makes this x squared instead of 4x, and that is probably going to change my ordered pair. I think the shape should be the same. There we go. Same shape. Going to be a different ordered pair though. Find that minimum. Left bound, right bound guess. Yeah, it's 1.400, 3.501. So the length of the side of the square that would give us the minimum area would be 1.4, whatever they want you to round to. Hee hee. Sorry about that. Everybody makes mistakes. Okie dokie. Moving on to the planes problem. Suppose we have two planes that are flying at the same altitude and are headed towards each other. One plane is flying due south at a ground speed of 400 miles per hour and is 600 miles from the potential intersection point of the planes. The other plane is flying due west with a ground speed of 250 miles per hour and is 400 miles from the potential intersection point of the planes. So what we're supposed to be looking for is a model that expresses the distance d between the two planes as a function of time t. So this is what we're after here, is this distance between the two planes. So remember, like, to find distance, we can use the distance formula. That's one way to do it. Or we can use Pythagorean Theorem. So if I look at the lengths here, the distances that the planes are from the intersection point, here's where this is the intersection point. That's where they might crash into each other, because this plane is headed this direction, this plane is headed this direction, and they're on a collision course. The distance between those two planes, if I label this, I'll just label it A, and I'll label this B. That's the three sides of our right triangle. So distance squared is going to be equal to A squared plus B squared. So now we just need to figure out that distance. Well, it's clearly like it's related to time, right? Because they're not just sitting still at 400 miles away from that intersection. It's also flying at 250 miles per hour. So this distance is getting smaller. So the length of this side, A, starts out at 400 miles, but then every hour it's getting closer by 250 miles. So I need to subtract 250 miles times however many hours they are flying. Similar with B. B is not going to stay 600 miles away. It starts out 600 miles away, but it gets closer by 400 miles times however many hours it's flying. So now our formula becomes d squared equals a squared would be 400 minus 250t squared, and then b squared would be 600 minus 400t squared. So then to get our distance, we'd have to take the square root of both sides. Now, for me, there's no need to FOIL this out. I see no purpose in it. However, my math lab is going to want you to FOIL it out. So I will pause this video and FOIL it out so you can see what the result would look like. Okay, so again, I really don't care if you FOIL this out. I think this version looks a lot nicer than this version, but my math lab will make you FOIL it out. So I've FOILed out each of these two binomials and then combined like terms. So that's what my math lab is going to expect for part A, which was to build a model for the distance. Then part B is the one that I'm the most interested in because it lets us use that model to do math stuff. So part B wants us to use our graphing calculator to graph d of t. So this right here, this is d of t. It's distance as a function of time. We're going to graph it and see how close they come to each other and at what time the planes are closest. So we got to put that in our calculator. Square root of 400 minus 250. The calculator doesn't know t, so we just use x. Plus 600 minus 400 x squared. And we'll go to a regular graphing, like a standard graphing window. See if we can see anything. I'm not seeing anything show up on my calculator. So when that happens, I like to go to the table and see what kind of values I'm going to get. Come on, buddy. Calculator table. Okay. So at 0, oh, that's why I can't see anything. When x is 0, y is 720. 1, 2, 3, 4, 5. So I need to make my window a lot bigger. So I'm going to make my y max a lot bigger, like 1,000, you think would get it? Well, look, graph. Oh, yikes, that looks like a giant absolute value curve. So here's what my graph looks like when I graph it. It goes down there and then goes back up. My scale is like ginormica. That window was, what was it? -10, 10, by negative 10, 1,000 was my window. You may not have to get that extreme on yours, but we can see what we need to. So remembering that each ordered pair that's on here has an x and a y coordinate. In this problem, the x coordinate, remember, was representing the time, and the y coordinate was representing the distance between the planes. So on this entire graph, where would the plane's distance be smallest? In other words, where would the planes be closest? Well, that's going to happen right here at this relative min. At that relative minimum, it's going to give us the closest the planes are to each other and also the time that that happens. So we just go second calc, find the minimum, and we want to do the left bound, right bound, guess. And that ordered pair is 1.528, 21.19998. So whatever they ask us to round to, we're going to round. And we would have to say that the planes are, the distance is this guy, so 21.2 miles apart after 1.5 hours. And that's the closest they come to each other. Let's see what we have next. Maybe we have time to do a couple more problems. All right. Here we have the time required to go from an island to a town. So we have this island over here, and it looks like we can either get in a boat and row across, or like we could row straight across and then walk straight, like making a right triangle, or we could angle our way across rowing and then walk the rest of the way to town. So it says it's 2 miles from the island straight across to the town. And straight across from here to the town is 12 miles. So let's see. Maybe I'll just draw a little mini drawing here. So here's our island. And then straight across to the shoreline is point P. And then from point P to town, it's 12 total miles from point P to town. But I might go ahead and row partway across. So if I row partway across to some other spot here and then walk the rest of the way, that's probably going to be my best bet. Because as we know, the shortest distance between 2 points is a straight line. So I could go straight across from the island to the town, which is a possibility. But I also know that I can row faster. Oh, I row slower than I walk. I walk faster than I can row. But I have to somehow get across. Like I can't just magically be on point P and walk the rest of the way to the town. So we're going to say that no matter what, I'm going to have to row some distance. Now, it might be straight across, but I'm just going to label it at some random point, and then I'm going to walk the rest of the way. So that random point, I'm going to label this point right here X. And I'm going to say that I am going to start a certain amount of distance from town because I know that it is 12 miles from the point across the river to town. I know that it is 2 miles straight across the river. And I know I can row 3 miles per hour, and I can walk 5 miles per hour. So the time t that it takes to go from the island to the town, let's get a formula for that. So we're talking about distance, rate, and time. The formula I usually use is distance equals rate times time. But my formula needs to be t equals. So I'll go ahead and divide both sides by r, and I get the formula distance divided by rate equals time. So essentially what I'm trying to put together is the total time that it takes me to get across is going to be equal to the amount of time I spend rowing plus the amount of time I spend walking. Because no matter what, I have to do a bit of both. All right. So for the rowing time, I'm going to need to do the rowing distance divided by the rowing rate. Well, I don't know the rowing distance at this point. I do know the rowing rate is 3 miles per hour. And the walking, I don't know its distance either, but I know its rate is 5 miles per hour. So we're going to have to do a little bit of figuring out to get this equation going. Okay. The rowing distance is this. The distance rowing is this length. And I've got a right triangle there with a length of 2 on that side. If I'm putting this point x, I could just label this entire distance to be x miles. And then I could use the Pythagorean theorem there. For my rowing distance, I know d squared would equal 2 squared plus x squared. So d would be the square root of 4 plus x squared. So I can put that in my rowing distance because rowing time is distance divided by rate. So I can put my distance here, 4 plus x squared. Okay. Square root of 4 plus x squared. Now the walking distance, if I'm going to row to a point that's x miles away from that p, if I'm going to row across here, then the amount of distance that I'm going to have to walk is going to be 12 minus x, right? Because this part of it is going to be x. The total distance is 12, so this will be 12 minus x. So my walking distance will be 12 minus x. And that's part A. Part A was to write that equation. Part B, what's the domain of t? So domain, in this case, our x values are the distance that point is away from the distance this x point is, where I row across, from that point straight across. So on B, domain is going to be x values. In this case, x is the distance from P to the point the person rows across to, the point the person rows to. I don't know how to better phrase that. So if the person rows straight across, that distance is going to be 0. So the shortest distance it could be would be 0. If the person rows just all the way into town, then the longest this x can be, if they go straight over to town like that, would be 12. So our x's have to be between 0 and 12. So that would be our domain, either in inequality, which you can put into set builder, or interval notation. Part C, how long will it take to travel from town if the person lands the boat 4 miles from P? So 4 miles from P, so I'm going to row across so that x is 4. So that's what that means, x equals 4. So here's P, here's the island, and I'm rowing 4 miles away, and then walking the rest. So x would be 4. So then we're just going to use our formula, t equals, and we put 4 in for x. And we can all work that out. I'm just going to leave that for you to work out. Part D, how long will it take if the person lands the boat 8 miles from P? So P, we're going to land 8 miles from town, 8 miles from across. So in that model, our x equals 8. So again, we just replace our x value with 8 and work that out. They could also ask us, where should we land the boat so that our time is minimized, but they didn't ask us that. So we don't have to answer that question. And that brings us to our last problem, which is the box problem. Promised you that this one would show up lots and lots of times. So we are making a box with a square base that's going to be made from a square piece of cardboard that's 24 inches on each side. And, excuse me. Whew. And we're going to make that by cutting out corners that are x by x in each corner. So here is the base of our box is down here. So that's going to be this part of our box. Okay. Then we have the sides of our box. This side over here is going to fold up and be this side over here. This side over here is going to fold up and be this side over here. Then we've got this flap, which will be that side of the box. And our last flap here, when we fold it up, is going to be this side of the box. So that's how we're creating the box. The original cardboard is 24 inches, and we're supposed to be expressing the volume of the box. So remember that the volume for a rectangular prism is length times width times height. Since this is a square cardboard, that makes it a lot easier to work with. But we need this to be in terms of x, which is the size of the corner that we're cutting out. So this side over here, this length over here, it used to be 24 inches, but I'm cutting off these lengths here to fold the corners up. So instead of 24 inches, this length over here is going to be 24 minus 2x. So that's like the length of our box, right? When we fold it up, the length will be 24 minus 2x. So we got 24 minus 2x for the length. And it doesn't really matter which side is the length and the width because it's square. So this side down here will say that's our width. And again, it was 24 inches, but then I'm cutting off x on each side so that I can fold it up. So this length here ends up being our width. It used to be 24, but we cut off 2 x's. So it's 24 minus 2x for our width. And then the height of the box, when I fold this flap up, the height of the box ends up being just this length because that's what I fold up to make it taller, to make that height. So the height is just x. So our volume formula becomes 24 minus 2x times 24 minus 2x times x. Now I'm guessing, again, like this is fine with me. I'm guessing that my math lab wants you to FOIL that out. So you would start by foiling these two together, and then you're going to distribute that x. So you would FOIL these two parentheses. Obviously, you're going to combine these like terms in here, then distribute your x through. So we'd have 576x minus 96x squared plus 4x cubed. Part B says, what is the volume if a 3-inch square is cut out? If we cut out a 3-inch square, then that means x equals 3. So our volume would be, we would just plug in 3. So 24 minus 2 times 3 is 6, times 24 minus 6 times 3. Or you could use this formula and then you just multiply that out. Part C, again, just ask you that low-level question. What is the volume if a 10-inch square is cut out? So we do the same thing. X equals 10, so volume would be 24 minus 2 times 10 is 20. 24, minus 20. That's a minus. And then times x, which is 10. But they could also ask you the more interesting question, which would be about like the maximum or minimum volume, depending on what our function looks like. So if I were to graph this, 576x minus 96x squared plus 4x cubed. Let's go zoom 6 and see if we can see anything. I'm guessing we won't be able to see anything because these are going to be big numbers. So I'm going to use my trick of going to my window or going to my table to be able to set my window. Table. Oh yeah, if x is 1, it's already at 484. Okay, so it looks like maybe I need to go up to a little over 1,000. So let's go 1,100 maybe. Oh, there we go. That graph has a maximum. So I could figure out how big to cut my flap so that I have a maximum value or a maximum volume, because right up here at that top, it would give me a maximum. So if I go from the left-hand side over to the right-hand side and then to my guess, the maximum volume of that box is, can you see that? 1,024, and it's inches. So volume is cubic, so 1,024 cubic inches. And it looks like I should cut that flap at 4 inches. It says 4.004, 00004. So that's going to round to 4. Okay. Good luck with all your story problems.